Hi, this is IvanBarnash with my explanation of assignment 4. So this assignment is about reducing overfitting with ConvNets. So let's get straight into it. For this assignment, I used the Cipher 10 data set. It has 60,000 color images in 10 classes. As you can see, airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So first, split it into training and testing subsets. After that, I normalized the data. I normalized the pixels so they were 0 to 252 because they're colored. And I normalized them to 0 to 1. Then I reshaped labels. And then I shuffled the data basically, right, for the models to not be able to memorize them by order. And I also create a small subset of validation to see how well the model performs on the unseen data during training. And then I have also the test subset to measure the final performance in the end. And also the training subset is kind of small, 10,000, to just show you the overfitting, basically. So then I took a look on the couple of sample images. As you can see, these images are very small. They're 32 by 32, and it will come back in play later when we cover data augmentation. But right now, let's just move on. As you can see here, I created some helper functions. So we'll be using 30 epochs and 64 batch size, and basically some helper functions for me to not rewrite the code each time. So now let's move on to the first model. First model being overparameterized CNN. We're not using any regularization methods here, and due to it having like a couple of dense layers, we can already expect a lot of weights, and a lot of weights, and most of the times means a lot. Means overfitting. Yeah. So we can see here 5 million weights, 5 million. Well, 4 million parameters. Way too much will overfit the model, inevitably. So as you can see, without any regularization methods, any regularization techniques, we can see that the training accuracy only rises to like 99% and validation accuracy stays on this 60% point. But the main thing is this gap we can see, overfitting gap, a clear sign of overfitting. And as you can see also the validation loss, it should decrease, but it only rises. A clear sign of overfitting as well, because it makes errors on the data it hasn't seen. Um, so now let's implement dropout and L2 regularization. So what is dropout and L2 and why do we need it? Dropout basically is a overfit and reduction technique that basically each epoch we have batches, right? So each batch we're gonna randomly turn off some neurons so that the model doesn't rely on certain neurons. And when it does rely on certain neurons a lot, then it will inevitably create overcomplicated rules. So we just force the model to generalize more, not relying on those neurons. Um, then L2 regularization. Basically, what it does is penalizes big weights. So big weights means a lot of importance on certain features. Means that basically we are balancing out the importance across the features instead of making the model rely on certain ones. Uh, it reduces the overfitting as well. It makes the model simpler and, for basically making it being able to create more general rules as well. So as you can see here, a lot less params, which is a great sign um, already. And as you can see here, the results are great because although the validation accuracy kind of stays, it is like 66%, right? And for the over parameterized, it was like 60, 61 or something. But it's not the point. The point is that the overfitting gap is almost non-existent. So they go along, which is very good. It means that over time, if there were more batches and more training data, um, the validation would like rise along with the training. Uh, um, I mean, the validation accuracy would rise along with the training accuracy, but in over-parameterized, it would create such overcomplicated rules that validation accuracy would only degrade or just stay at the same point, and the training accuracy would only rise. So as you can see here, the validation loss only increases as well as the training loss. This is what we need to see. This is a good sign that there is no overfitting. It creates less and less, it makes less and less mistakes on the data it has never seen before. So now we're going to implement the data augmentation. What is data augmentation? Basically, data augmentation adds variance to the data. As you can see here, in this example for images, it basically flips the image, rotates the image, translates or zooms it randomly. For other data sets, obviously it would be like different. For example, for audio, it would like, I don't know, add some kind of noise in the background, maybe change the tone, maybe, something like that. But for text, for example, it will like flip the text maybe, but keeping it readable. But for this one, it just does things to the image. But basically, how it reduces overfitting, it reduces overfitting by adding variance to the data, right? Adding more variance to the data means the model will create more general rules to recognize it. But as I said, the thing about the images about this data set, as you can see, the graphic here is quite jumpy because it constantly rotates the image, constantly like flips it and stuff like that. So each epoch it might like have spikes in validation accuracy, then you have some drops, spikes and drops. But the main thing that we need to see is that overfitting um, overfitting gap is almost non-existent here as well as in the you know simple regularization. But why is it jumpy? I think it's because the training images amount is kind of small, but also that it's only 32 by 32 pixels. So the images are small too. So this may impede, and I mean the images are small and they're like a zooming in, rotating. It can reduce the amount of needed details. So and seeing that the images are already small, for example, if you would if you wouldn't tell me this is a cat, I wouldn't be able to tell anyway. Like me too. So um, yeah, I think that's why. But what we need to see here is that the overfitting gap is almost non-existent as well, and the validation loss steadily decreases rather than increases, although it is jumpy as well. But the thing is, I think for this data set, it might not seem beneficial, but overall, this is a very good technique to reduce overfitting because adding variance always, makes difference in a good way, right? Because making variance to the data means um, it will create more general rules. This is just the reality. So now we are comparing results as you can see here, and I also plotted some graphs. So as you can see, test accuracy here for each model, but the main point is the overfitting gap. This overfitting gap basically means that over time, over parameterized model will not improve its learning skills, like will not improve the accuracy on the data it has never seen before, but these will because they are not overfit, right? They're constantly improving on the data it has never seen before. They constantly create more general rules. So in conclusion, as we can see, the first model basically it has uh, too many weights. So over-parameterized ConvNet, it can perform well on training data. It will anyway perform worse on validation and test data on the data it has never seen before. And the dropout and O2 regularization, data augmentation, these are very good techniques to reduce overfitting by making the model learn more general patterns, which the exact thing we need for a good model. Thank you for watching. Goodbye.